Yeah, I always see Hebrew homeworks.
I will show you. You see the board?
Lecture slides.
Well, I'm in that class.
Lecture slides.
No, so here, look, there is, first of all,
He's very.
lecture slides, lab slides, and this is the Zoom connection which we're using right now, which is also the good or bad news, we have observers. So please be on your best behavior.
What are observers?
We have other students that are here observing you.
Oh.
So be very good.
Is this
Also, the good
Argentina?
news, also the good news and the bad news is that I decided that the lab will not be required attendance because since the girls don't have to come, it will be unfair to make you have to come. So
That's okay, but the lecture.
the lecture is also not required attendance. You can all go home.
But I don't want to go.
But if you go home, if there's nobody here, I don't. So there won't be a recording.
One guy, yeah.
There won't be a recording.
There's one person here.
So that's the bad news is also I'm not going to tolerate hooligan behavior. If people are talking when they shouldn't be or getting up and moving around, I will ask them to leave and I will refuse to teach until they do leave.
We'll be doing that a
So I'm
lot.
warning you, I'm not going to punish anybody until he's been warned, and you've been now warned. If you want to talk to me, you can ask, you can raise your hand is the best. So go ahead.
We will have a lab homework due at Thursday at 5 p.m. every week.
Yes.
In addition, we will have a lecture homework to do as well.
No, there'll be a few lecture homeworks, but there won't be that many. There'll be
And
like
you'll let us know when you.
there'll be like 3 of them or something like
Oh,
that.
right. You'll let us know when they're.
Yes,
due, when you.
yeah.
Thank you.
The lab information is 30% of the final exam also. In addition to being 30% of your grade,
The lab what is?
the information that is taught during the lab will be on the exam. So therefore, and it'll be also, I think, 30% of your grade. I don't remember exactly the number, maybe 25%, but 25% of your grade will be based on the lab homework and the homework of the lecture. The lab homework and the homework of the lecture is 25% of your grade, all the homework together. 75 is the exam. The exam will cover 75 or 70% of it will be from the lecture and 30% will be from the information taught in the lab. So all that information is supposed to be known by you. But attendance is not obligatory. That doesn't mean you will have any good chance of passing the course without attending, but I'm not going to require you. Okay, so these are the lectures, the lecture slides. These are based on the book Operating System Concepts by Silberschatz and Galvin. I think this is Galvin. I'm actually using the 9th edition. There's a newer edition, I think the 10th edition. It doesn't really matter to me which one to use, but I'm recording it. Yeah, and I want to put this slideshow. Okay, slideshow from current slide. So the book is actually in the library, both here and at Tal. And actually, can somebody who's near that thing lower the angle of the camera a little bit? But they might have me in it. Just a tiny bit.
Heavy. I thought you pointed the light.
There, just a little bit. Yeah. All right, that's good. Oh, yeah, a little bit more, a little bit more. All right, perfect. 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 Thank you. Now they can see a tiny, like 6 pixels of me walking around there. Okay, so the thing I have to say about the book is it's very good. The book explains very nicely. It's used all over the world, and it's better than even I am.
Can we find this book?
It's in the library. You can follow it. The chapters that I have here are the same chapter numbers that are there, except 5 and 6, I think, are reversed, but you'll figure it out. It's a very good book. You don't have to read, in general, the end of the chapter, it deals with more advanced topics that I won't necessarily cover. So it's really just good. So you don't have to read the whole book. You have to read each chapter, the first main sections. And then towards the end, it starts going into specific cases like how exactly Apple works or how exactly Microsoft works. And those things are all out of date by now. So there's not really much point in getting too much into them. Question?
Is the dinosaur gonna relate to any of the material that?
No, it's just nice. For those people who came just now, standing in the back, I have some good news and bad news. Good news is you don't have to, none of the classes, including the lab, are going to be required attendance. But if you are here, I expect you to be quiet and in your seat. If you are not, and I'm warning you now, if anybody is not capable of doing that, I'll ask them to leave and I won't continue the lecture until they do leave. So I'm not going to tolerate any bad behavior on your part. It's I don't have, you don't have to be here, you can leave. If you want, I don't think you'll do very well in the course, but you might if you're not here. So I suggest you do come, but that's up to you. Also, I also announced the homework. You can ask your friends what that is. Okay, this is lecture 1. And what we're going to talk about is what is not, for example, well, let's just start here with what is an operating system, since we're doing an operating system, so we should ask that question. A program that acts as an intermediary between the user of a computer and the computer hardware. Right? A computer is hardware, but we want an easier way to access the hardware than through directly accessing it. So we have an intermediary program, essentially, that does the hard work for us. And that's the operating system. That's one of the things it does, but it does many, many things. Here are some goals of an operating system: to execute a user's program. When you run your program, you type the name, you have to tell the operating system, run my program. It should run it then. Make solving user problems easier, make the computer system convenient to use the computer hardware in an efficient manner, maintain security and protection between running programs, allocate resources. The last two is actually the main focus of the course, which is security and protection. Well, which is that your programs, one program should not affect another program. Security, I guess, is that people shouldn't log in, shouldn't access your files. But protection means that the behavior of one program shouldn't adversely affect the behavior of another program. If I have 2 programs running, I don't want that because one program crashes, the other program crashes. I want them to be separated. The other thing is allocation resource. That's an important topic, which is we've got the CPU, for example. That's a resource, and we need it to be allocated between all the programs that are running in some kind of fair or possibly unfair by priority way. We need to establish ways of divvying up all the resources. There's other resources other than the CPU, for example, memory. The memory of the computer has to be, and also the hard drive has to be allocated. So the job of the operating system is to do those things. If you think back to your course, Introduction to Computer, in hardware engineering course, in the computer architecture course,
For MIPS.
in MIPS. You think back to that, you were the only program running on the computer at the time that you ran. When you were in the MIPS world, it was just your program. So you had all the memory at your disposal and nobody else could interfere with you. Now, all of a sudden, we have to think about where there's multiple programs running on the same computer. Okay. So here we're going in more detail about that. OS is a resource allocator. It manages all the resources, as I said. It decides between conflicting requests for efficient and fair resource use between processes. Right, if 2 processes both want the CPU, it has to decide who gets it. And we'll see, I mean, just to give you a inkling of where we're headed, for example, time sharing is a concept. Time sharing means that I get the CPU, one program, I'll call it myself, whereas I, as a running program, will get the CPU for 200 microseconds, and then the next process running on the computer will get the CPU for 200 microseconds, and then back to me and back to him and alternate. That would be one way of divvying it up. The operating system is a control program because it controls the execution of a program, prevents errors and improper use of the computer. Right, it won't let you do certain things. For example, usually a program won't let you alter the operating system itself. Probably one thing you shouldn't do. Other kinds of improper use, it tries to prevent. It's kind of like a policeman. More discussion of definition. There's no universally accepted definition of an operating system. One definition is everything a vendor ships when you order an operating system is a good approximation. In other words, when you buy a computer and they installed on it Microsoft Windows, then all that's on your computer is the operating system. That's one definition. Of course, that includes things that really are tangential to the operating system. Things like a browser might be installed, or Zoom might be installed. But that's one definition. Another definition is the one program running at all times on the computer. Right? When you shut down everything, if you shut down the operating system, you shut down the whole computer. But if you shut down any other program, anything you shut down and the program will still, and the computer will still run, then that's not part of the operating system. But we say that's called the kernel. In other words, the most essential part of the operating system, let's say, is the kernel. Everything else is either a system program, which is what ships with the operating system. Now, a system program means, like, for example, Task Manager. you don't need task manager, which we learned in the lab, we use task manager. You don't need that to run an operating system. That's a CLI, that's a tool for the user to manipulate programs, but you could have an operating system without that. So that would be called a system program. And then there's application programs that would be something like if it came with a browser. Browser is also something you don't necessarily need, but it's not related to the system. It's an application that a user uses. All of those things are less, are not really the kernel. Now, they're not really the kernel. Now, what I wrote, ND is me there. I wrote the one program that manages, controls, and provides services for all the other programs running on the computer. That's also an easy way to think about it. Okay. Computer system structure.
You're grading the exam.
I'm writing the exam, grading the exam. Yeah, you're the only people taking the course this semester.
I mean,
So
so
here-
your definition, then we'll get the point.
Yes, yeah. I might ask you, what are 3 definitions? Please, I don't know who's talking, but if you came late, I have a rule here. There's no talking in the class unless you want to talk to me. You have to raise your hand. So please participate. I don't want any craziness in the class. And again, I'll say that attendance is not mandatory, it's neither here nor in the lab, but if you are here, then I expect you to be a good student, which means asking good questions to me and not to you. Yes,
In the last lab, we just went through the slideshow. Will it be like that in the future, or is it work on the assignment, or is it both, or?
no, it's gonna be basically mostly a lecture.
Mostly
Mostly a lecture every single lab. And I said, as I said to the people who are here on time, I said that the information of the lecture, the information of the lab is 30% of the final exam. So notice the exam is not just on this lecture, it's also on the lecture of the lab. So essentially you have like a 5-hour lecture in the class. Okay. Well, yes.
Did you write all the previous exams for operating systems?
I write them all?
Yeah,
No.
are the previous systems gonna be the same as this one, or is it will be different because you're writing it? It'll be different because he's doing it.
Every exam will be different. I don't repeat anything.
But you're really asking me, are they useful to study?
They're for sure useful to study from, but I don't guarantee that the style will be the same. I don't have no obligation. I can do whatever I want.
You're like the dictator.
No, the exam, in fact, should be a different style because why should you be testing your knowledge, not your ability to do this kind of exam? Computer systems can be divided into 4 components. So here are the 4 components of a computer system: hardware, operating system, application program, and users. The people, the machines, or other computers, right? Because other people can use a computer, and also machines can use the computer. But what are the first ones? Hardware provides basic computing resources. For example, this is this keyword resource that we talked about: CPU, memory, I/O devices. What are I/O devices? Input/output devices, like your screen and your keyboard. Memory, you should know what memory is: the RAM of your computer,
SRAM.
not the. When I say memory, we don't mean a hard drive, although that would also could be on the list here. Operating system. Okay, we said already, controls and coordinates the use of the hardware among various applications and users. Fine. Application programs define the ways in which the system resources are used to solve the computing problems of the user. So, I mean, that's a very technically correct definition, but what it means is the program, right? An application, it defines the way I'm using those resources to get some goal. My goal is to have a document printed that's a letter to my mother. So I use Word, that's the application that uses the resources of the computer to get me my goal. So for example, word processors, compilers, web browsers, databases, it's fine. Go on. This is the introduction to the course, so it's not such heavy material, but we'll get heavy. Here are the 4 components of a computer system. You see the users, you see the system and application programs, the operating system, and the hardware. And the user uses the application, which then uses the operating system to get to the hardware. So there's a kind of a layered approach, and you can also see that the hardware is like, smaller, so it's almost like wrapped around it. That's why actually there's something called a shell, which is something around that's sort of it's a system program, but it's sort of in between the operating system and the application, and they call it a shell because it kind of wraps around the inner part, which we call the kernel, right? So the kernel is the seed, and the shell is what's around the seed. So there's a program called a shell, which if you take the course in Unix, you'll learn programming shell.
Wait, is kernel?
And also in Windows, they have shell. They have what they call PowerShell. Yes.
Kernel is in the OS or the system programs?
Kernel is in the operating system. Kernel is the essential part of the operating system.
We have a course for Unix, so we learn shell scripting and stuff like that.
Yeah, there's a course in Unix where we learn shell scripting. Yep. Okay.
100% correct.
What what do operating systems do? Users want convenience, ease of use. They don't care about resource utilization. In other words, they don't care if the resources are being utilized in a good way or not. They just want the computer to be easy to use. But shared computers such as mainframes and servers must keep all users happy and cordoned off. That's what we talked about. Cordoned off, I said, protected from each other. In other words, if I have multiple users on a server, I don't want one to be able to corrupt the files of another. Users of dedicated, so in other words, and that presents a non-ease of use. That's a contradiction to ease of use, because that means I need passwords and I need protection, and I can't just go wherever I want in the computer. Users of dedicated systems such as workstations have dedicated resources, but frequently use shared resources from servers. So therefore, a workstation doesn't need as much protection as a mainframe. Handheld computers are resource poor, as they have slower hard drives or slower CPUs and smaller memory usually. So they're optimized for usability and battery life. We talked about that a little bit. Battery life is also a consideration. You don't necessarily want the fastest CPU because it'll drain your battery. Some computers have little or no user interface, such as embedded computers and devices in automobiles. Right? You could have the computer. There could be a computer that automatically, checks something in your car and tells you that you're that you're low on oil, but that computer that's doing that, it doesn't have a user. It has a display, not much of an interface. I can't really talk to it. Actually, in cars, you can open up a little panel and connect a computer to the car, and then you can start talking to the car. That's what the mechanic does when he wants to figure out what's wrong with the car.
Maybe a thermostat that you don't interact with.
What used to be done by just mechanical means is now done by computer means. But this is called an embedded computer. It's an important term to understand. Embedded computer. If you take the course in Handasat Tochna in software engineering, we'll talk a little bit also about embedded systems. Embedded systems means a system that is for a specific hardware, like a plane is the best example. Protected. So what else does operating systems do? They protect and separate processes from each other. So here we're introducing the word process. A process is a computer program that is running and using resources currently, as opposed to a program that's sitting on a hard drive not being used. Once it's running, it's in memory, it's using the memory resources, it's using the CPU use resources, but they need to be separated from each other. You don't want one process disturbing another process. Give each process the feeling that it has the whole computer to itself. Right? The process shouldn't really even know about the other processes. I mean, if it wants to, it could maybe find out about them, but it should be able to run without having to take into account what other processes are doing. Each one runs independently. There's something called a bootstrap program. A bootstrap program is basically the program that loads the hard drive, because if you think about it, who is going to get the hard drive running? The hard drive is sitting on a hard disk. Sorry, I was said the wrong words. Who's going to get the operating system running? The operating system is sitting on a hard drive, but who's going to run it? So you could say the operating system itself should run itself, but that's a contradiction. It's impossible. How could the operating system already be running in order to boot itself up? So you have another program which starts the process going. Now you can say, well, who starts that? So that one is started automatically when the computer turns on. It looks for a particular, it used to be the first section of the hard drive, and it runs a very small program, and that program starts running, and that program, you can tell it which operating system I want. And therefore, you can have a computer with what's called a dual boot. You can have a computer that when you run the bootstrap program, it asks you, do you want Windows or do you want Linux? And then it can load up either one, because neither one has been loaded yet. But that program has been automatically loaded when the computer turns on.
Bootstrap program and bootloader is the same?
Yeah, yes. Bootstrap program or bootloader is the same thing.
Is that like BIOS?
Yeah. BIOS is an example. Typically, so where is this stored? It's not, if it comes with the hardware, so therefore it's not stored on the hard drive. If I don't, I could buy a computer without a hard drive, it still would have the bootstrap program. And BIOS would still be there. I could take a computer, take all the parts out, all the memory out, all of the disconnect the disk and turn it on, and a program will run. Where is that program sitting? It's sitting in ROM, read-only memory, or today EEPROM or double EEPROM, a certain kind of it's basically called firmware, but it's built into the hardware. And it initializes all aspects of the system, loads the operating system kernel, and starts execution. Fine. So now computer system organization, computer system.
What's firmware? It was the read-only memory, or what's firmware?
Well, we call generally known as firmware.
What is firmware?
Firmware is, well, it's not software and it's not hardware. It's in between. It's
I've not heard of
firmware,
that.
because that's why it's called firmware. And firmware is software essentially that comes with the program, with the computer when you buy it,
Thanks.
stored in ROM. It's that little program that gets the computer running. One or more CPU device controllers could, yes, question.
The operating system is not in the bootloader, the bootloader just tells the other places in memory to start up.
Yeah, you couldn't fit it in, the operating system nowadays is like gigabytes, so it's on the hard drive. But the EEPROM is very small, could be kilobytes.
And there's reserved addresses in memory that cannot get changed that are saved for the operating system.
I don't know what you're referring to.
Like, because the operating system has to be somewhere, so how do you make sure that you don't replace the information of the operating system itself
Well,
in memory?
who's you when you say you?
The user,
The operating system is, operating system is running as soon as you run the computer, right?
yes.
So the operating system will protect itself. We'll talk about that. It's something called kernel mode and user mode. You have to be in kernel mode in order to change the kernel, in order to change the operating system. So this is so here we're just showing you that all of these different devices, all these different things, these different parts of the computer are all using memory. And they're connected to memory through something called a bus. So a bus is what allows all of these things access to the memory. I don't know if we talked about it in computer architecture, but it is a topic sometimes taught in computer architecture, which is how you can have multiple things on the same connected line using a tri-state device. But in any case, the idea is that the data is transferable from the CPU to memory, from disk controllers to memory. All of them have access to memory. And the mouse or the printer that you may use is connected to a USB controller. And that's a device built into the computer that knows how to communicate with these different devices and with the CPU and to use memory. And so to the monitor it has to connect to a graphics card or graphics adapter in order to communicate with the CPU. The CPU doesn't talk directly to the monitor, it talks to a piece of hardware built for talking to the monitor. So another important principle, actually, we're going to get to later in the course, is that the I/O devices and the CPU can execute concurrently. That means that if the CPU is busy doing some mathematical operation, right? In this picture, the CPU is doing something. That doesn't mean that the disks can't be being read for some other process. I could have one process calculating the square root of pi or something, and the other one is reading a file from the disk. And this controller is in charge of taking care of that reading process. So therefore, the CPU is free to do some other calculation. CPU is not directly involved in the reading of the disk. When eventually the file is read from the disk, the CPU may be notified that the file is ready, and then it will stop its calculation of pi, or not, but it'll eventually stop its calculation, and it'll attend to the task of taking care of that file. Yes.
So they all can talk to memory at the same time on one.
No, they can't all really talk to
So
memory
it's
at the
not
same time.
At the same time.
It's not at the same, that's what I was talking about.
Real fast.
That's what I mentioned about a
Tri-state.
tri-state device. Only one, they're all connected to it, but only one can get through at a time.
Okay, so they're switching super fast all the time.
They're switching super fast.
Cool beans thing.
Okay, each device controller is in charge of the particular device type. So that's what you see in this picture. Every device has its controller. Each controller has a local buffer. When you buy a computer, sometimes it tells you how much like cache the graphics card has, how much internal memory it has. In addition to your regular memory, there's memory for all of the device controllers. So that, for example, if I'm reading from the disk, I'm just reading it into my own local memory until the CPU is available, and then the CPU says, okay, now I'm ready to take your file, and it transfers it into the main memory. So each device controller has a local buffer. The CPU moves data to and from main memory and to and from local buffers. But the CPU's job is to say, move this section of memory to there, move memory around. So again, if I'm reading the disk, it goes into an internal buffer here. When the CPU is finished calculating the square root of pi, and I've told them I'm ready, the CPU will now take this memory and copy it to the main memory. We'll learn later that there's something called a DMA. Actually, we probably learned already in your course in computer architecture. There's a DMA that can do the job of copying the files, copying the bytes. Okay. I/O is from the device to the local buffer of the controller. That makes sense. The input output is to the local buffer, and then later it goes from the buffer to the main memory. Device controller. Let me finish this next sentence. Device controller informs the CPU that it has finished its operation by causing an interrupt. That's what I was saying, a notification. When the device controller has got the file that you asked to read in its local memory, it has to interrupt. It has to stop, send a message to the CPU. I'm ready. Question, somebody have a question?
Yeah,
Yeah.
you go over what the buffer is again, the local buffer.
Well, you don't see it in this picture, but imagine a little piece of like this kind of memory in here and in here, and well, even in here, this cache memory in the CPU. And that's because we want these things to be able to work in parallel. We want them to work at the same time simultaneously. They need to have their own little bit of like local storage, so that they can store things locally until the CPU is able to say, okay, now copy it. So they have their own memory. But we're talking about the interrupt here. We're going to talk about it more, also a lot more in the course. But an interrupt is what we call that moment when the hardware tells the CPU, I'm ready for you, I need your help. So interrupts and the operating system. So this is actually a new slide that I created. Operating systems are interrupt driven, which means, what does that mean? It means if there are no processes to execute, no I/O device to service, there's no processes in the computer, there's no I/O device that's got anything to do, and no users to whom to respond, an operating system will sit quietly waiting for something to happen. In other words, it's not like a program that you write to calculate, that somebody just calculated an unknown prime number, which has like 42 billion or million decimal points. And it took him like 10 years to let the computer run to calculate that. So that would be a program running. So the operating system would be involved in that. But if there's no program, there's no process, which is a program that's running, and no I/O device and nothing, so then the operating system is sitting there quietly, not doing anything. That's the way, at least in theory. I mean, right. You say, well, wait a second, I look at my Windows and it's always got something going on. That's because they've added things. They've added, let's say, something that checks if there's updates, or they've added a virus checker that's scanning your files all the time. There could be things running all the time, but if we think about the pure definition of an operating system, it is just not doing anything. And even those programs actually are started at a certain point. At a certain point, it says, okay, now start scanning these files, and then it finishes, and then it says, so those are also interrupt driven. Basically, all programs are interrupts to the operating system saying, start this program. If you type the name of a program and hit enter, then that generates an interrupt, tells the operating system, please run my program. So the operating system is interrupt driven. It wouldn't do anything if it didn't get an interrupt. Interrupts transfer control to the interrupt service routine to be run. So when the interrupt happens, there's different, let's say, numbered interrupts. If interrupt 17 happens, then program, we call it a routine, but you can think of it as like a function. It's the same thing. A function gets run for that interrupt. Software can generate an event or an interrupt. There's like lots of words that we use for the same thing. Interrupt, event, we also call them exceptions and faults and traps. But I'm going to try to explain the difference. So software can generate an event, and then it's called an exception. For example, if an error occurs in a program, you divide by 0, or you try to access memory you're not allowed, that doesn't exist. It's beyond the limit of the memory. Right? You try to go to memory place 10 billion, and you only have 5 billion memory spaces. So in all those cases, but that's the software is doing that. The software divided by 0, the software tried to do that. That's called a software generated event. And that's called an exception. This is an unintentional exception and is called therefore a fault. That's the term for it. A fault is when you have a fault. You didn't plan on dividing by 0. I mean, you shouldn't. And you shouldn't try to go to memory that doesn't exist. So those are faults. If the program intentionally asks for the operating system service, in other words, if he says, I want now to read a file, then that would be called running a system call. Furthermore, another example of asking the operating system is I put a breakpoint trap. In other words, I'm doing debugging of my program and I put a breakpoint there. So what's going on? The program is running and I said, when you reach this line, stop. That's an interrupt. That's interrupting the normal flow of my program. So that's also an example of something, where did we say? That's also an example of a trap, we're calling it. And a privileged instruction. I try to do something that requires super user privileges. All of those are not faults because they're perfectly legitimate. I may want to stop my program in the middle to check for debugging purposes. I may want a system call to read a file. And I may want a privileged instruction. So then it's not called a fault, it's called a trap. But both of them are exceptions, or types of exceptions. I'm just trying to make clear these terms that you might see.
A trap is also an exception.
Yes,
Is it a type of exception?
I think it's a type, that's what I'm saying. I'm saying, well,
The something of the.
the way I'm thinking, you're saying that these are identical?
Yeah.
And that this is a third type?
I would say they're both types of interrupts, but I don't see why a trap would be an exception.
Well, it's an exceptional case. No, it's like, it's exceptional in the sense that it's not an error, but it is exceptional. It's not the normal flow of the program.
I understand. Yeah, exceptions and 2 types, one is a fault, one's a trap, one's unintentional, one's intentional.
That's what I said. That's exactly what I'm writing here.
Yeah.
Tell me your name again, Eitan?
Now,
Eyal.
Okay.
I knew it started with A.
Okay, we call him
Something course.
Yeah.
we call him Atom too.
They call Eyal.
Now we do.
Anyway, so Eyal, you might be also right. You might be, the things that different people might think of them differently. You might be right that an exception is not a trap, but I'm saying that an exception has 2 types. Hardware interrupts are asynchronous. They're caused by, what does it mean? What do we mean by asynchronous? They don't happen in the flow of the program. These things all happen in the flow of the program. Even my divide by 0. I eventually got to the line where I divided by 0. That was in the flow of the program. And also I eventually got to the system call or to the breakpoint. Those are all in the flow of the program. So those are software generated. But hardware interrupts are asynchronous, which means they don't happen in connection with the flow of the program. They're caused by events external to the CPU, caused by devices. What's an example of that? When does a device cause an exception? When you press the key, you press a mouse click, you press the X in the corner of the window to close the program. That's external to the flow of the program. It's a mouse click.
that's still software though.
Well, mouse click is hardware.
Yeah, but specifically for the program pressing
How-
the X.
How the program reacts is its own choice. I could write a program that if you press on the X, maybe it doesn't close, theoretically, I don't know. I don't know, that's, anytime you're using hardware, that's what I wrote here, devices. Devices means hardware, a mouse, a keyboard. Example, a network card alert that a packet has arrived. right? You have a network card that's talking to the internet that says new data has arrived. So it tells me the clock, there's an internal clock in the computer. Every computer has a clock in it. And the clock may notify the CPU that another microsecond has passed. Every time there's a microsecond passing, it notifies the CPU. The power supply notifies that electricity is about to go out. Right? I unplug the, I don't know, I turned off the computer. That's pretty serious hardware interrupt. Okay. Now here is an interrupt timeline. This is saying like this: the CPU is running a user program, and there's going to be an IO interrupt. So here comes the program, and it says IO request. Now the IO device had been idle when it was over here. This means that when the line is over here, it's idle, and here it's transferring. So I come along and I say, I want some IO. So that takes some time, but eventually the IO's device starts transferring data. When the data has reached its buffer, it's now ready for me to copy it. So the transfer is done. Interrupt is signaled. And when the interrupt is signaled, the user program stops running. And now we have the IO interrupt. The program now gets the file. Now this is all. Now it's all idle here until again the interrupt is handled. He runs, and there's another IO request at some point. And again, the IO device becomes active. And when he's finished, he notifies this program, and the program now goes into the state of IO interrupt processing. In other words, he's dealing with the fact that the data is ready, so he's processing that data. Here, the user program was running normally, and here it's handling the response of the IO request that he made over here. Okay, so that's like this, that's like the relationship between the CPU and the IO device. And the point is that at this point, the CPU can be used, the user program could be running while the IO is running. Neither of them are idle. So what happens when you handle an interrupt? In, for example, a system call. We said there are different types of things here. One of them was a system call, or system call here. So what happens in a system call? First, there's a jump to a specific location. In other words, I have to run special code. I have to run special code to handle the system call. What system call is it? Is it system call 1, 2, 3, or 4? If you read from a file or write to a file, what am I trying to do? So I have to run to that code. Now, when I run to that code, I have to save the old SP value. What is this SP? The stack pointer. Because the program had, it's now, we're going to keep track of all the data that it's stored in the stack. So I've got to save where it's pointing to, switch the stack pointer to the kernel stack. Now make the stack pointer of this process. This process is now going to run kernel code. This is actually a weird idea, but basically your program, there's a process that's your program. We're going to kind of hijack your program, and it's going to run code that you didn't write. Your process is going to stop running whatever code it was running, and now run different code, the code that the operating system has for that particular system call. But it's still your process. It's not like another process doing it. Your process is now, you've requested to now run some kernel code. So you've got to point to the stack pointer for the kernel. You've got to save the old PC value, because you got to remember where you were in your program when you were finished to come back there. Save the old privilege mode, which means whatever privilege mode I was in, let's say I was in, for now we're just thinking about two modes, user mode and kernel mode. So user mode means I can't access, I can't do privileged things. I can't run operating system code when I'm in user mode. So I save the old privilege mode. I save the fact that I had been in user mode, and now set the new privilege mode to kernel mode, which is mode 1. So now I'm in this other mode. My same process has now been like elevated to the level of being a kernel process, so that he can execute lines of code that are part of the operating system, that are part of the kernel. Because that's what I asked to do.
and sets the PC, sets the new, I think it's supposed to be, the new PC to kernel system call handler for that system call. In other words, I want to run the code for the particular call that I made. I made a call to read from a file or to write to a file. So those are different lines of code. So I've got to move the PC to where the system call handler, the function that handles that system call, that deals with that system call, is located. I've got to save the call save registers. Remember in MIPS, we had the S registers and the T registers. T were temporary, S were save registers. So we've got to save all the call save registers, all the S registers, because I might now be running a program. I'm not running a program, I'm running a function, let's say, that's a kernel function, but he's going to use the same registers, they're physical hardware. So I got to save the call registers. Now I finally perform the handler. I run the actual code of the operating system. Now I finished doing whatever he asked. He asked to read some file. I told the IO device to start reading it. And now I can come back, restores the call save registers, restores the privilege modes and the stack pointer and the program counter. And I basically start running the program again. So I'm just showing you how I can jump to do a system call and come back, and I have to change the mode so that when I'm running the lines of code that are the system call, I'll be able to. Because it's actually a hardware check. Just a second. It's actually a hardware check. If I try to run system lines of code without the mode bit being set to 1, then the hardware will not let me. The hardware will interrupt me. We'll talk about this again later, of course. But basically, there's special hardware that prevents you from running kernel lines of code. Yeah, question.
Just gonna ask about the mode thing again, meaning, can you explain privilege mode?
The privilege mode, basically, we don't want to let, remember we said that we don't want to let processes access directly the operating system and screw it up. But how are we going to, what about when a process says, I want the operating system to work for me, to do something for me? How do we do that? What we actually do is we let the process itself do the action that he's asking for, and we elevate him to be equivalent to the kernel by changing his mode to kernel mode. And we essentially, and the way it's done is actually there's a bit in the hardware that gets turned on. Questions?
Yeah, where do we save all the information, the stack pointers and the registers? Where are we able to put it somewhere else to?
Yeah, good question. Where do you think we saved it?
I would have thought like the registers, but then you said that we have to overwrite those as well, so we save them somewhere else.
I would say that right here, we change the stack pointer to the kernel stack pointer. So now we have some area in memory that's reserved for the kernel, and we can copy anything we want there.
Got it, thank you.
Okay. So actually, I think this slide sort of explains the same thing again. And that previous slide I added. This is, I think, the original slide. Dual mode operation. That's what we're talking about. When we say dual mode, we mean to say there's user mode and there's kernel mode. That's what I was talking about. Allows the operating system to protect itself and other system components. So we have these two modes. There's a mode bit provided by hardware, as I said, sort of a review of what I said before. Provides the ability to distinguish when the system is running in user code or kernel code. In other words, I can only run kernel code if the mode bit is lit. We said this, there's such a thing as a privileged instruction, only the kernel can do it. System call changes mode bit from kernel. This is like a shorthand version of what I said before. Increasingly, CPUs support multi-mode operations, which means you don't just have kernel or user, you have another mode, which is useful for virtual machine managers, because when you want to have, like, let's say, multiple operating systems on the same machine, you want let's say I'm running. Here, I'll give you an example of this. I mean, this looks like a line here that you could just say is a throwaway sentence, but what is it? What's behind this line? So I have to explain a little bit what's behind this line. But let's say you're running Windows on your computer, and then on top of your computer, you want to run Linux. So Linux has for himself a concept of user mode and kernel mode, right? But when I go to kernel mode in Linux, am I in kernel mode in Windows? Maybe not. Maybe I'm in user mode the whole time. Maybe I'm in user mode from the perspective of the underlying operating system, which is Windows. This program is some other program, and it's called Linux, and I don't know anything about it, and it's always in user mode. And then when I go to user mode, when I go to kernel mode in Linux, maybe I'm still in user mode. So we need to, so instead of doing it like that, we have three modes. We have three modes, and then the Windows will sort of let me do some operations when I'm in that third mode. The Windows will let me, because I need to read to a file, so I need to get to super user mode. I need to get to kernel mode, but it won't let me do others. So there's a kind of a third mode. Okay, I didn't really explain it too much, but I gave you a kind of an inkling of what the idea is. The idea is that because we have multiple operating systems at the same time, we may need to have more modes. Here's just the same thing that I just said in words. This is a picture of it. Here we are, we're running our program, going along merrily. We say system call. We say system call. Why does it say trap? No, see there, he calls it a trap. What did I call a trap? I call it trap when it's intentional. Yeah, system call.
Yeah.
So we're okay. So he goes in a trap. The mode bit is put to 0. Here he's calling 0 being kernel mode. Now I can execute the system call. When I finish executing the system call, I put the mode bit back to 1 and go return from the system call. But the point that most students don't understand here is they think that the kernel is doing this. They say, oh, the kernel is doing this and my program is doing this. But then if the kernel is doing it, I wouldn't need to, like, it's not that the kernel is doing it. You're doing it as the kernel. There's lines of code that are kernel lines of code. You're executing them.
The students probably think that because it's in the blue box.
Right, it looks like that.
It's like Kiddush Levana. You're not davening to the moon. You're davening through the moon.
I mean, it's semantics. It's semantics at the end of the day. If my process is running kernel code, then essentially at that moment I am the kernel. So you could say I'm the kernel is doing it.
So the user process.
The user process
Crap, switches the mode.
and becomes the kernel. Yes. Okay. All right, I'm here to talk about this. The DMA again that you guys remember from. Quiet, please. The DMA we remember from architecture is used for high-speed I/O device, right? It's used for high-speed I/O devices able to transmit information at close to memory speeds. So when we want to copy, guys, I don't want to talk over you. When we want to copy a large chunk of information sequentially, one byte after the other, a block of information, we can use the DMA. We don't have to have the option of the CPU copying each byte. And that will allow us to copy much faster. Device controller transfers blocks of data from the buffer stored directly to the main memory without CPU intervention. Only one interrupt is generated per block rather than one per byte. If the CPU would be doing copying, there would be interrupt for each byte. But with the device controller, we stop once, we say copy from A to B, a whole block, and then we can go about our business. The CPU can do other things while the DMA is busy copying. All right, by the way, this is like a quick overview of many topics that we're going to see in depth later. So it's not like that's not the end of the discussion of interrupts, and now we're talking about a whole other topic, storage structure, which is going to be discussed again in chapter 10, but we're just mentioning it now.
It's like an intro.
This is the first class. This is the first class of the course.
Thank you.
This is the first class of the course, so I'm showing you where we're going. But it's important actually to have these ideas in mind because sometimes it's hard to understand a concept without understanding another concept. And then you can't understand the other concept without understanding the one. You need to have, and each one helps fill in the picture. So I need to sort of do a review. It makes sense that they do a review of the whole course.
So it's bootstrapping,
What?
so it's bootstrapping the course.
Maybe you can say that, yeah.
Yeah.
Main memory,
That's a
okay.
point on the final, come on.
Here, let me start with the picture because the picture is clearer, but we have a pyramid of memory speed and size, essentially. Registers are the fastest, and there's the smallest. We have very few of them. Cache is another kind of memory. It's physically built differently from registers. It's cheaper and therefore can be a little bit larger, and it's not quite as fast. Then main memory is very fast, but not as fast as the others, and it's larger. Solid state disk, like a flash drive, would be slower than main memory and cheaper. And then you'd have a magnetic disk, like a actually moving hard drive. And then you could have an optical disk, which would be like a DVD or a CD. They still exist. And then the slowest, but the cheapest, would be a magnetic tape. Magnetic tapes are actually, well, last I checked, which was a long time ago, you can still buy a magnetic tape. They're used in backups. When you want to, let's say, copy every single byte on your hard drive. You just want to have an image of your hard drive in a storeroom somewhere in case there's a fire in your house, you'll have everything you had. So then you don't care how slow it is, but you want to be cheap because you don't want to, why should you spend extra money? You want to take the disk and put it somewhere else. So you just copy the whole hard drive onto a magnetic tape. So that would be the slowest, cheapest. So now I'm going to the previous slide and the storage structure. So main memory was the third thing in the pyramid. Is the only large storage media that the CPU can access directly. Yeah, I guess you could say that's true. In order to get to the cache, there might be well, that's an interesting question.
Cache isn't large storage.
It's not large. Maybe that's what he means. Okay.
So, yeah.
Maybe that's what he meant. The main memory is random access. And it's typically volatile. What does the word volatile mean?
There's no electricity, it's forgotten.
Volatile means that when there is no electricity, the memory is not preserved. Random. What does random access mean? What does random access mean? Does it mean I randomly access things? Just random?
It's not.
You don't need each part of it, okay, to sort of.
I can go to each part. Yeah. Better definition. Any more definitions?
More definitions.
What does it mean, random? I want a more clear definition. Random access. What does it mean? I mean, on a disk drive, on a tape, I can get to any part of the disk also. I can get to any memory.
In the middle, you have to go from where you are.
Ah, thank you. Tell me your name.
Yoda.
Yehuda? Yehuda said the best definition. The best definition is the time it takes to get to any particular byte is equal to the time it takes to get to any other byte. On a tape, you have to spin till you get to the end. On a hard drive, you also have to spin till you get to move ahead. That's the definition. Random access means the access
Memory
is not dependent on my location.
Means you can start anywhere.
I can start anywhere and the
You
time,
can start using those bytes to.
the speed of access is the same.
Cool, thank you.
All right, if you have a question, you can ask me. I can clarify. Secondary storage, extension of main memory that provides large non-volatile storage. That's your hard drive. So we call that secondary storage. That would be your hard drive or your flash drive. Magnetic disks, that's one example. They're rigid piece of metal or glass platters covered with magnetic recording material. Disk surfaces logically divided into tracks, which are divided into sectors. We're going to talk about this in chapter 10. The disk controller determines the logical interaction between the device and the computer. In other words, the disk controller will keep track of like where the file actually is that you want. It may be on different tracks. I mean, your file may not be contiguous. You know the word contiguous?
Nope.
No.
Contiguous means it is one location. Contiguous. Like the 48 of the 50 states of the United States are contiguous. They're all touching each other. But there's 2 states that don't touch any other state. And those are Alaska and Hawaii. They're not contiguous. So the memory is not contiguous on the disk, and the part of the job of the disk controller is to determine the logical interaction between the device and the computer. Solid state disks faster than magnetic disks are non-volatile, so we're talking about the flash drives. So that's the pyramid that we saw here. Storage hierarchy, speed, cost, volatility. In other words, these, like I said, are slower. These are actually, the lower ones are are not volatile, the top ones are volatile. Until here, the first three are all volatile.
So when you say main memory in our computers, that's RAM, and then solid state disk is my like terabyte on my computer.
Yes.
Cool.
Feature SSD.
Caching, what is the concept of caching is copying information to faster storage, which means I may have a copy of main memory data in my cache. And then it's faster to access it now. But I won't put all of main memory in cache because its cache is by definition smaller than main memory. I can't put it all. Device driver for each device controller to manage I/O. So every kind of device has to have its own controller to manage the interactions, to manage the input and the output. It provides a uniform interface between controller and the kernel. Yehuda and Nachum, you can't have a private conversation during my class. Caching, important principle performed at many levels in a computer. In other words, it's not just the main cache. There's the main cache for main memory, but there's caching in each device. There's many caches. Like when you buy a graphic, when you buy a graphic processor, right? GPU, graphic processing unit, it has cache also. There's many places that there's cache. It's not just one cache. It is information used directly from the cache. If not, data is copied to the cache and then used there. Cache is smaller than storage being cached, right? The storage that you're caching is always going to, caching means that I take some of the data that I have and I put it into my cache memory, but not all of it. So it's always small. There's always going to be a cache size, which limits how much I do, and there's going to be a replacement policy, which we talked about a lot in architecture. I have to decide what goes in the cache, what doesn't. Okay. Now, this is something I also added to the course because it's like a concept that you may have heard of.
Oh, the ALU.
Let me talk.
I just missed it.
This is called the von Neumann computer architecture. Basically, all computers today pretty much are following the von Neumann basic blueprint. And I just want you to hear that term because you shouldn't graduate from computer science without having heard that term and know what it is. They say things like, is it like, I think they say, is it von Neumann compliant or no? Oh, something else. That's something else. Sorry, that's a different term. But anyway, our computers are von Neumann architecture. What does that mean? We have a main memory, we have some kind of control unit, and which is the CPU essentially, and we have a arithmetic logic unit, and then we have input and output devices. So there's 5 components. Input is like the keyboard, and the output is like the screen, and the CPU. We have these different parts. That's the basic structure of according to von Neumann, and that's what we know and love. Okay, what are the details of it? A processing unit that contains an arithmetic logic unit and processor registers. So in here, where are the registers? I don't see a picture of the registers. They're really small. A control unit that contains an instruction register and a program counter. Right? An instruction register means where we are in our program. And a program count. Well, no, that's instruction register is the actual instruction that we're executing, and the program count is where we are on the program. Memory that stores data and instructions. So the actual program is over here in memory. That's the data and the instructions are in this box. And external mass storage usually, which I don't think is in this picture. It's not in this picture. But usually there's an external larger storage, like a hard drive. Input-output mechanisms. The term von Neumann architecture has evolved to mean any stored program computer in which an instruction fetch and a data operation cannot occur at the same time because they share a common bus. Remember that picture of the bus here?
Yeah, well,
There's a common bus. So when I want to get data from memory,
and I wanna run the CPU, I can't do them both at the same time. Because they're both using the same bus. This is referred to as the Van Neumann bottleneck. Why is it called bottleneck? Because I have to wait for the memory, which is always gonna be slower, to finish before I can do an instruction.
You have to like wait for what input to be put in before actually processing the next part of the program or something. What's
In other words, I have to withdraw a line of the program in order to run it. So I gotta wait for the read of that line, and then I can run it, and I gotta read another line, and I can't run while I'm reading. Right, I can't take an instruction from memory. Is a very nicely said, and I can't run it at the same time.
But you have pipeline.
Exactly, how is pipelining gonna work? How does pipelining work? Because if they're both using the same bus, how can I read a memory at the same time as I am executing a command?
I don't know, only people who.
I got every pipelining question wrong.
Well, we have to have
Pipelining is gonna.
separate, well,
Pipelining is within the CPU, it's not within a bus of the whole program. I mean, pipelining within a CPU where it's running different parts of, different parts of the CPU are doing different things.
yeah,
Whereas this, having one bus between the input, the output and the CPU and the memory.
but instruction
Sure,
read
sure.
is the first stage. Instruction fetch, IF. It's the first thing, so we actually are reading from memory.
Right, you have fetch of one instruction, you can run that fetch, you're gonna run the fetch, but you've already fetched something beforehand. That you don't have to wait. Because that instruction is not on the CPU, it's not on the bus. And so while it's in the CPU, you can fetch another thing and send it on the bus because it's not in the bus in the CPU. And that's how.
At some point you fetched it. What was going on when you fetched it?
There was something in the CPU already beforehand, and when you open the program, nothing was in the CPU, and so it went to the CPU and
Alright.
it wanted something.
I'll take what you got, but I need more, I didn't think about it.
What's the accumulated?
It's also a problem, it's also a question that bothered me, I didn't quite understand. How this bottleneck seems to contradict the idea of pipeline, but I'm sure while I'm talking, somebody will look it up and tell me a better answer. Most systems today use a single general purpose processor. Like a CPU. Most systems have special purpose processors as well, like a graphics card or a graphics GPU. Multiprocessors and multi-core systems growing in use and importance. Well, that was true 10 years ago. Now it's already the main thing that people have. The multi-core refers to a single CPU with multiple execution units. Now, basically, you can think of it like this. What's the difference between multiprocessor and multi-core? Multiprocessor means that you have two actual chips that you take off the shelf and you put them in the motherboard and you connect them. Multi-core means you have one chip that you took off the shelf, and in the chip itself, there are two CPUs. It's whether it's mini processors built into it. It's basically how it's sold. Is it sold as one unit, or did you combine two units that were produced separately and put them together? If you put them together, then it's multiprocessor. If it was produced as one unit with two processors in it, then it was multi-core. Because remember, a computer like HP isn't creating its own chips. It's probably buying chips from a company in Taiwan that's producing the chips. And then the question is, are they buying two chips for them and then combining them together, or are they buying one chip which has two processors in it?
So more chips means two buses, and like two cores means still one bus?
I don't think no, I don't think so. I think, maybe, I don't know. It's a good question. I don't know.
Okay.
I don't know.
Is there any practical difference then between them?
They all race the same.
In
It
general,
just
I mean,
feels like-
practically in general, multi-core is probably faster, but I don't know if there's, I don't know if which one, much more than that. Yeah.
Does this count? Is this like an abstraction of a von Neumann architecture or an entirely different thing?
No, it's still I just sort of stuck in Van Neumann into the Van Neumann. I don't think it's mentioned in the book, but I just stuck it in. It's not that this is different from Van Neumann. It's still Van Neumann.
It's
It's
just an
just
application of it.
This is a Van Neumann, you have, maybe you have two control units, but it's still a control unit. It's still Van Neumann. What would not be Van Neumann? Well, could be an embedded device that's like, it may be
Anything with more than one bus, right?
anything with more than one bus, I guess wouldn't be. But also some kind of computer that's not if it maybe you could build an embedded computer that didn't have input or output, it just did things, for example.
Or if it just had entirely separate hardware for the instructions and for data.
Okay, yeah, that would also be. Okay, so anyway, most of them have these multi-core refers to a single CPU with multiple execution units. That's what I was explaining. While multiprocessor refers to a system that has two or more actual CPUs. Multi-cores have multiple cores or processing units in a single CPU. Multiprocessor contain multiple CPUs, just repeating itself. Okay. Advantages are different. Advantages include, once you have either of these things, you're gonna have increased throughput, you're gonna have economy of scale, which means that you now could add more memory and your computer will run faster. Whereas when you have one, there's a certain point, if you have like one CPU and you add more memory, you're gonna hit a wall. As you keep adding more memory, there's a certain point where you add more memory and it's not gonna get any faster. But if you have two CPUs, then that wall is further away. So you have better economies of scale. Increased reliability, graceful degradation, fault tolerance. What do we mean by what's graceful degradation? If you have two CPUs and one of them breaks, you might not even notice it. Your computer will still run. You'll still be able to run it, maybe a little bit slower, but you might not even notice. So it's called graceful degradation. It degrades, but it's not like now it doesn't work. It still works. It's getting slower. So you have increased reliability. Here's a picture of multiple cores. Here you see that they're using the same bus to get the memory. And these are, but they all have their own caches. See, the cache actually, if it makes it that the bus is less. Once I've got the data into cache, it doesn't matter that we have a shared bus because I have this cache here. I can run my program purely through cache. Right? If I have all the data that I need in cache, then I don't need to go to main memory. I've got everything in cache. So I can run here, and these ones can all run independently without ever talking to main memory because they only talk to main memory once in a while when they need to get new data for their cache. They have their own internal cache, and therefore the fact that they share a bus doesn't slow them down. This is
When you get like a bunch of race conditions and terrible stuff like that. Like if they're both trying to change the same place in memory or read the same place in memory and they add data.
yeah, well, the programmer needs to right. If they're separate programs, if each one is a completely separate program, then the operating system will divide them and give them, you have memory location 1 to 10, you have 20 to 30, and you have 60 to 70. So they're all in different places, if they're different programs. If these are all using this, if there are multiple threads, which we haven't talked about yet, but if it's one program that's spread out over these three, then we could have race conditions that we need to, and the programmer will need to manage that.
The operating system?
No, the program. The program. Okay, here's a picture. What's the difference between that picture and this picture? This picture, there's no blue. In this picture, there's blue. What does the blue mean? The blue means that this is the thing I bought from Taiwan. I bought this chip. I bought this thing together.
These things work concurrently or sequentially?
Concurrent.
But how does it know where, like, what part of the process one core is up to versus the other?
No. So I'll tell you, this is a very important point you're asking. You're asking how do we divide my program into these two things? If I have a program that's calculating pi, it's just one program that's calculating pi to 1 billion decimal places, it's gonna either be here or here. It's not gonna be in both of them.
Yeah.
It's my job as a programmer to say, wait a second, I got 2 cores. I'm gonna divide this work up into 2 separate tasks, and I'm gonna make 2 threads. And then the operating system can separate them.
But it doesn't do the same task on multiple cores.
Exactly. One thread will be here and one thread will be there. And it's my job to decide what each thread does.
Okay, thank you.
You can't, right? It's a big misconception. People think, oh, I have in other words, here's an exam question. If I have a multi-core computer and I'm running a program with 1 thread of execution, will it run faster if I have 2 cores, or 1 core?
The same.
And the answer is the same. Assuming all other things are equal, it'll run the same because I can't reap the benefits of 2 cores if I only have one execution running, because it's gonna either be here or here. One, it's called a thread of execution. Yeah,
Are we gonna go over threads? Cause
yeah, there's a whole chapter on threads, yeah.
yeah, just you wait, buddy, just you wait.
Yeah, the truth is, again, in a Unix course, we actually program threads.
Wait, so can you explain the practical difference? Because
I don't think there's much practical difference.
Because, yeah, here also you have multiple threads without the dual.
I don't
quotes,
think
like,
there's
you
any
do
practical-
The exact same thing.
From my perspective, there's no practical difference.
Okay,
They're just two different things, they're two different terms, and they describe two different things. And as a user, as a user, they're the same.
okay, cool, good to be on the thing.
Operating system structure, so here we're talking about how we divide up the CPU between programs. So something called multi-program, which we've sort of been talking about for really without realizing it, multi-programming is the idea that you have one CPU, back to one CPU. Think in terms of, most of this course actually, you're going to be thinking about one CPU. So imagine I have one CPU, but I have two programs running at the same time. So based on everything that we learned now, we learned that the CPU can run at the same time as the IO can run, right? The IO can be running. So if I have two programs running and one of them starts doing some IO and he can't continue until he gets his IO back. He's doing a hello world. So hello world means that I'm printing HELLO, etc. to the screen. That takes an enormous amount of time from the perspective of the CPU. The CPU can do a million things while that's going on, while the H gets written and the E gets written, and all those things get written to the screen takes a long time. So that's called an IO operation. So if I would just have one program, the CPU would be idle while the hello world is being written. But if I have two programs that both want the CPU, what I can do is the minute the one program says, I want to write hello world to the screen, the CPU can say, oh, I'll give that command to the IO device, to the IO device controller, and let him print it. And now I'm available. Why don't I go and service the other process that wants to run? If I run the operating system like that, then that will be called multi-programming, because I'm running multiple programs at the same time. What determines when I switch from one program to the other? Only one factor: whether a program asks to do IO or not. When a program asks, when a job has to wait for IO, for example, the operating system switches to another job, to another process. And then he'll keep running that other process forever until that other process, even if the first process finished his IO hello world and now wants to print something else, or now wants to calculate pi, he won't come back to him until the second process also goes to IO. If the second process never goes to IO, then he'll finish the second process. And only when he finishes the second process, he'll come back. So that's called multi-programming. When I switch based on IO, single user cannot keep the CPU and IO device busy at all the time. Single user or single process cannot keep the CPU and the IO device busy at all times. And I'm going to keep one busy, but then the other one is going to be available. The minute I go to IO, then I start using IO, CPU is available for somebody else. Multi-programming organizes jobs, which is the same thing as processes, code and data. There's the code and the data is working on. So the CPU always has one to execute. A subset of total jobs in a system is kept in memory. Right. We don't have, there's a concept called
Like the number of
switching. Wait, swapping. In other words, there could be, let's say, 15 processes that all want to run. It could be there's not enough memory in the computer to run all those 15 processes. So it'll keep 4 of them on the hard drive. They're not running at all, but their code and their data has been copied over to their hard drive. The other 11 are now competing for the CPU. And then those are, and then which one gets it is called job scheduling. In other words, I'll have to determine when the CPU is now available. I have 10 jobs that are waiting. One job is on IO. 10 jobs all want to use it. Which one gets it? I have to have a scheduler. That we call job scheduling. And this is all where the only method that I divide up the CPU's use, I distribute the CPUs based on IO. Question? Still correct?
Yeah, no, I think.
Okay, now we can improve upon multi-programming and add another reason to interrupt. Because remember what I said, if a program never goes to IO,
and it's 11 jobs that all wanna get the CPU. And a program never goes to IO that has it, then all the others have to wait until the first program finished. So we might say, let's do something called time sharing. Or it's also called multitasking. It's called multi-programming, it's called multitasking. But it's also called time sharing. It's a logical extension which the CPU switches jobs so frequently that the user can interact with each job while it's running, creating interactive computing. In other words, like I said before, 200 microseconds. Every 200 microseconds, I switch, let's say, from one job to another. So even though a job hasn't gone to IO, if 200 microseconds have transpired that he's had the CPU, then I'm anyway gonna go to the next job.
In timeout.
So I'm gonna time out, exactly. So this is like more fair. Everybody gets their 200, every second, everybody gets their 200 microseconds. And then we do a round robin, we come back to the first one. And everybody gets a fair amount of the same time. Now, if one process got his 200 microseconds, and then he, after 100 microseconds, said, I want to print hello world. We're not going to give him, we're going to send his message to the IO device to print, and immediately go to the next guy. So he'll, in fact, have only used the CPU for 100 microseconds. Because it's not like you get your 200 microseconds to do whatever you want with them. You get to do CPU processing with them. The minute you go to IO, you have to, you lose your CPU. You can't keep the CPU just because your time isn't finished. So it's the first, whichever comes first. If your time limit ends, or you went to CPU, or you went to IO, whichever happened first, that's when there's a switch being made, and the other process starts running.
It always does this time sharing thing,
Well, if you're running a multitasking computer, then yeah.
and so if I want to run something really complicated, it's only gonna be running it.
Yeah, on Windows, it's time sharing, and on Linux, it's time sharing. If you have a browser running at the same time, and you're calculating pi, if you close your browser, your pi will get more time of the CPU and run faster.
Like how many jobs? I assume there's like thousands of jobs happening.
There could be thousands,
And
if
so
there's thousands
if
of,
each one gets 100 microseconds, I feel like I would have noticed that it slows down a little.
well, maybe the number is 10 microseconds. The number is not, I'm just throwing out a number.
Okay,
It doesn't have to be 200 microseconds.
and is there no way to allocate more? Because
Yeah, of course.
You could have, in theory, you could do anything you want.
okay,
And we're in a course of theory, so yes.
okay.
But in practicality, I don't think Microsoft does that with their Windows.
Okay, listen,
So practically each program, like regardless of its importance, is getting the same share of time.
Yeah.
So there isn't like, oh, this program doesn't really matter, let's give it what type of.
No, that, it wouldn't be class, it wouldn't be time sharing, then it would be priority. It would be based on priority, and that wouldn't be the same concept. Okay, everyone's with me? Response time should be less than 1 second. In other words, if I say, if I type in, if it has a C in a C program and it asks for, let's say, a username, and I type in my username and hit enter, I shouldn't wait more than a second before I see a response. So if there's too many jobs and it's causing the time, by the time I finally get to my 10 microseconds or my 200 microseconds has been more than a second, then I have too many jobs running. And then what I'll do is I'll take some jobs out of the system and I'll put them on hold. But I don't want a system that is so slow just because I have lots of jobs.
Are we breaking for Minfo, by the way, at 4?
Yeah, remind me at 5 to 4.
Okay, that's.
I'll remind you.
That's the moment.
Isn't
No, please.
let's just finish this slide
Okay,
and then we can
My
go.
phone will start thinking.
So the response time should be less than a second. Each user has at least one program executing in memory. I don't know why we say that exactly. Each user has at least one. I mean, otherwise he's not using the program. Otherwise he's not on the computer. If you're not executing anything, then you're not there.
Alright, it's 5 to 4.
Let me finish this slide and then we'll go. If several jobs are ready to run at the same time, then we need to do CPU scheduling. CPU scheduling means it's the same thing we talked about job scheduling over here. In other words, several jobs are ready to run at the same time. Now, I explained that time sharing is a round robin. We keep like first in, first out. First guy there gets it, and then the next guy, according to whichever jobs when they were started, or by their start time. But it doesn't have to be like that. I could have a priority scheduling where certain job will get it. If he's in line, then he gets to go straight to the head of the line. So that would be CPU scheduling. So it doesn't have to be based on time that you got there. First in, first out. If processes don't fit in memory, swapping moves them in and out of memory. That's what I said. If we don't have enough space in memory for all the jobs, we can swap them to the hard drive. But then they can't run. Then they're sitting on a hard drive waiting to run, and then they're a job, but they're not a ready process. They're not a process that's ready. They have, if at some point in the future, the number of processes decreases because the program's finished, then we'll swap them back in, and then they become a ready process. Virtual memory allows execution of processes not completely in memory. So you could have a process that's very large, that requires a large amount of memory because it's a lot of lines of code. Let's say it's 1 billion lines of code, so it's many, many bytes. I can't put it all in memory. So I put part of it in memory, and part of it is still in the hard drive. That's called virtual memory. If I use the hard drive as if it's memory. All right, we'll stop there. We'll come back. We'll come back. Yeah. More.
We played till 8:30 today.
We haven't shot it there.
No, it's not. It's just some fun. We have data searching steps. Algorithms.
Benji. Yeah, I get.
Okay. So we're continuing, we were talking about the difference between multi-programming and multitasking. And we said that multitasking is a division of time, but you could also have a priority queue. The queue of people being given that time could be based on priority, but you usually, and it could also be, yeah, but there's other different ways. We're going to talk about it in much more detail. Different ways of dividing up that time. This is what we call CPU scheduling. Okay, let's go on. Memory layout of a multi-program system. So if you're not using the MIPS simulator and you have multiple programs running at the same time, then you have to, first of all, divide up the memory. So if this is my memory, 512 megabytes, I guess. So the operating system will take up a certain section of the memory, and then the rest of the memory will be divided by job 1, job 2, job 3, and job 4. And exactly how much to give each job at the beginning is also a question we'll have to think about in the continuation of the course. But each one will get its own area of memory, and that has to be done by the operating system. Process management. A process is a program in execution. Well, we said that, I think. It is a unit of work within a system. In other words, what do we mean by unit of work? We mean that the more processes that a system can run, we can say the system is working harder, or that it can work harder. If it is running a lot of processes, then it's working hard. If a system is very powerful, how do we measure that it's powerful? That it's capable of running a lot of processes at the same time. Processes obviously need resources to accomplish their tasks. CPU, memory. They need to use the CPU. They need to use memory. They need to use I/O devices. They need to use files. Well, that's a kind of I/O device. That's a thing on the access through an I/O. Initialization data. Right, there may be certain data that it starts up with. Process termination requires reclaim of any reusable resources. Right, if a process is no longer running, then obviously it's memory. If, for example, here I have 4 jobs running. If job 2 finishes, then this memory is now available for some other job. I need to reclaim the memory. Single threaded processes has one program counter, specifying the location of the next instruction, as we know from our class in computer architecture. Process executes instructions sequentially one at a time until completion. Okay, we should know that. Multi-threaded process has one program counter per thread. If you have multiple threads, that means that the process is essentially running in tandem, multiple activities, then you can have a program counter for each activity, even though you have one program. You have one program, but one thread is at this line of the program, another thread is another line of the program, and they're running in tandem at the same time. Typically, system has many processes, some users, some operating system running concurrently on one or more CPUs.
Right, there are usually gonna be many processes, there's gonna be an operating system, there's gonna be a user. Concurrency by multiplexing the CPUs among the processes. So we can also have real concurrency, not just simulated concern, right? When we talked about multitasking, it was really simulated concurrency, because everybody got a small section of time and then they got it again and again and again, but there was gaps. But you didn't notice the gaps because they were so fast. But you can have real concurrency by having multiple CPUs. So what are process management activities? The operating system is responsible for the following activities in connection with process management. So these are the actions that it has to do. It has to create and delete user and system processes. It has to suspend and resume. All right, I get it. Hello? Hello, yes? No. Okay. So the system needs to create and delete both user and system processes, suspending and resuming process, right? If you stop the process, you need to resume it again. You need to provide a mechanism for processor synchronization, which we're going to call semaphores. And as if you have multiple processes using the same memory, we need to synchronize them so they don't ruin the data of each other. So you need some kind of synchronization, providing mechanism for process communication. One process maybe wants to signal another process or share data, providing mechanisms for deadlock handling. There could be a deadlock where, let's say one process is waiting for the other to finish, but the other is waiting for the other to finish. So they're each waiting for each other. That's called a deadlock. And such a situation, neither process will ever finish. So you need to, that's one of the things that the operating system needs to think about solving. Memory management, another thing that the operating system needs to do. Again, this is an overview of all the things the operating system needs to do. Data must be in memory before and after processing. Right, we need to be able to keep the data. We don't want to destroy data. Instructions must be in memory in order to execute. You can't execute a program if it's not in the memory, right? You can't execute a program that's on the hard drive. It has to be first brought into memory in order to execute it. Memory management determines what is in memory when optimizing CPU utilization, computer response to users. In other words, what is memory management? It's saying that we take some of the data, which is before and after, it has to be put into memory. We take the instructions, some of the instructions, and put them into memory, and then we run the program. So there has to be a management of the memory. How much things are going to put in memory, what we're going to take out, what we're going to put in. Those are things that the operating system needs to think about. Memory management activity, for example, keeping track of which parts of memory are currently being used and by whom. Well, that's kind of like this. In other words, you got to keep track that job one is over in this part of memory and not in this part of memory. Somebody's got to keep track of that. Deciding which processes or parts of them or parts thereof and data to move into and out of memory. That's what we talked about process swapping, where if there's too many jobs in memory and the program is running and the computer is running slow, I might suspend one of the jobs and put them onto the disk. That's called swapping. That's also part of memory management. Allocating and deallocating memory space as needed. It could be that while a program is running, it all of a sudden needs more memory. So I need to give it more memory. And then I need to take away the memory if it needs less memory. And another topic that we're going to talk about is file system management. File system management, files usually organized in directories. We have directories for the files. We have access control, which means that I can't look at somebody else's files if we're different users on the same computer, because his files are not accessible to me. Or for example, the operating system maybe has to be able to create and delete files, right? If you can't create a file, then your operating system is not going to be very useful. Primitives to manipulate files, directories you can remove files, rename files, all those kinds of things. Mapping files onto secondary storage. You need to know where the mapping needs to locate. We need to be able to locate a file. So a user asks for a file, we need to be able to find it on the hard drive. Backup files onto stable, non-volatile disks like the hard drive. Mass storage management, that means the hard drive, we do manage the hard drive. Usually disks used to store data that does not fit into main memory or data that must be kept for long periods of time. Right, we obviously gonna have things on the hard drive, somebody needs to manage the hard drive. Proper management is of essential importance, the entire speed of the computer operating on a disk subsystem and its algorithms. Your computer will be very slow if your hard drive is mismanaged. I mean, obviously, also if your hard drive itself is slow, but even if it's fast, but it's mismanaged, it can be slow. So what are some of the operating system activities? Freeing up space, free space management, which means keeping track of what space on the hard drive is not being used so that I can use it. Storage allocation, actually assigning a certain section of the hard drive to a certain file. Disk scheduling, that means if I've got multiple requests to read different files, I've got to schedule them. Which one goes first, which one goes second? I can't read two files at the same time from the disk. But I might have two processes that both want to read a file. So I need to schedule the disk reading and writing, yes.
These are important for SSDs and HDDs, meaning if it's mechanical, it's much.
Yeah, you need to still read and write.
But it is because
It doesn't matter what kind of disk it is, you still need to read from it and write to it. And you need to manage it. What?
Because it's not mechanical, it's actually.
It's faster, but it's still not 0 time. Some storage need to be fast. Some storage need not be fast. So there's the slowest kinds of things, which is like magnetic tape, for example, or optical storage. Still must be managed by the operating system and applications. Varies between read once, read many times, and write and read. Write once, read many times. So there's something like EEPROM is electrically programmable read-only memory. You write it once and you read it many times. Some stuff is read and write many times. Different kinds of memory. That's not so important. See where we're going. Yeah. Okay. So migration of integer A from disk to register. So we're just like the life of an integer. You have to use, this was a topic that we talked a lot about in architecture. You have to use the most recent data. You don't want to use the wrong copy of data. So the original data is on the magnetic disk. The value A gets moved to main memory, then from main memory to cache, and then eventually to a register. And I may manipulate it here in the register, and I got to be sure to write it back all the way back down. I can't just change it here and not change it in cache and main memory and magnetic disk. Multiprocessor environment must provide cache coherency. So that's the concept of cache coherency. It means that the cache is correct. What's in the cache is the same thing as in the register and the same thing as in main memory and in the hard drive. And must give me the most correct value of the cache, the most recent value. Cache needs to be invalidated. So there was another, which means that it's no, you have to know that if something changed, if something changed in main memory, then I've got to reread the cache. If somehow I'm sharing data, let's say some other process is changing the data, I've got to reread the cache. So there's a programmer, I don't know, a long time ago, a guy named Phil Carlton, I don't know exactly who he is, but he said a famous quotation. There are only two hard things in computer science: cache invalidation and naming things. Naming things means naming like functions and classes. What should you call it? Because it should really describe what it is. And the other thing is cache invalidation, which is being aware when what data is in the cache is no longer correct, then you have to invalidate. Distributed environment situation, even more complex. What do we mean by distributed environment situation? That means that, like, if you have multiple servers using the same database, like you have multiple copies of the same database, and let's say one program changes the database here, how does the other one needs to have to also know about that change? Okay. One purpose of the operating system is to hide peculiarities of hardware devices from the user, for example, I/O devices. In other words, if I change my computer screen, I don't want to have to change the way I wrote my program. Right? I want my program to still work, even though if I go from one kind of screen to another kind of screen. That provides me like an abstract screen, an abstraction of the screen. So how does the operating system do that? Well, because we have a uniform language of talking to a device driver. I am an operating system. I talk to device drivers in this language. The device driver's job is to translate my request into the type of request that the hardware actually needs to get. So I'll always talk to device drivers in the same way. And the device driver knows to change my request to what it needs to be for that particular hardware. So the operating system is hiding the peculiarities of the hardware. As a programmer, just type C out, and the operating system translates that correctly. I/O subsystems responsible for. So what does the I/O subsystem do? The device driver, let's say, memory management of the I/O, including buffering, caching, general device driver interface, drivers for specific hardware devices. When you make a new piece of hardware, you have to write a device driver, and then that device driver has to be installed in the operating system. And the operating system has to use that device driver to talk to your thing. So it becomes essentially part of the operating system. The device driver becomes a part of the operating system.
That's like the drivers that you need for your printers and things.
Exactly. That's a
it's
device driver.
converting the code into something the hardware recognizes.
Right, he's like, the device driver is allowing the operating system to talk to the device, because because I could create a new device tomorrow and I still want to make Windows be able to talk to it. And Windows, when it was written, didn't know about this device. So there needs to be a uniform way that Windows talks to device drivers, and the device driver knows how to talk to that particular machine. So there's two concepts we talked about before: protection and security. Protection is a mechanism for controlling access of processes or users to operating system resources not allowed by the process. That means like the operating system has to protect one process's data from another process. It can't be that one process can invade the data of another process. For example, back to that picture here, this is the best example, is that like, if this process whose data is supposed to be here tries to write to this data, he just tries to write to this location. He knows the location. It's number 4,000. But he writes there. The operating system needs to tell him, you cannot do that, because it's not your data. So that's what we mean by protection. Security is a defense of the system against internal or external attacks. And there's a huge range of attacks, including one which is called denial of service, which is theoretically, very hard to protect from, because if I'm a server, I'm designed to provide service. How do you do a denial of service attack? You basically ask for the service many, many times. If I go to a website and like try to download the web page 1 billion times, then somebody else who tries to download it may not get service because I'm busy. He's busy trying to handle my requests. So such an attack is called denial of service, because I'm denying other people service by requesting service so much myself. And it's kind of hard to protect against that, because I'm in the business of providing service. I can't just not provide service when you ask. So what they do is if it's on the same computer, we won't let them access more than once. So then there's something called DD OS, which is distributed denial of service, which means I use multiple computers to all request the same page, for example. And then it's harder to detect. Worms, viruses, identity theft of service. Okay. Systems generally first distinguish among users to determine who can do what. So we have such a thing as a user ID. We have such a thing as a group ID, and well, the user ID is making sure that I'm the user who, like whenever we create a file, we say who is the owner of that file.
and we give it a user ID, an ID that is associated with the file, and says that user number 113 is the owner of this file, and if user number 114 tries to access the file, we'll say you can't, we'll deny you. So we need to create user IDs and process IDs. So that, well, process can't access a file that's owned by another process. There's also thing is a group ID, where we can group users together and say anybody in this group can have access to a file. There's something called privilege escalation, which allows a particular user to elevate his privilege to become, let's say, a super user, which means he's on the level of the operating system, so he can access any file. So you want the operating system to allow that possibility, maybe with a password. If you know the right password, you can elevate your user to become a super user so that you can access files. That's a service that we need to provide. And we're also going to talk a little bit about virtualization. Virtualization is, I don't want to get into all the things written here, but virtualization just basically means that you have one operating system natively compiled for the CPU. And he then runs other operating systems as guests. So for example, you could have a VM where running Windows XP guests, each running the application all native, all on native WinX host. In other words, you could install Windows XP onto your computer, and on top of that, virtually run other operating systems. You could also have a specially designed operating system to put on top of it other operating systems, and that's called and that's what VMware usually does nowadays. VMware is a company that produces a facility where you can put what's called a hypervisor. I think it's called a hypervisor, which is basically a very basic operating system, and on top of it, you put multiple operating systems, and then you can go from one to the other. So you can have on your system, you install this kind of operating system, which its whole purpose is to just allow other operating systems to be on top of it. And then you could have first with the hypervisor, and then you put Linux and Windows and something else, and then you can switch between them. That's called virtualization, because virtualization, why is it called virtualization? It's not you're not really running the operating system on the machine. You're running it on top of another operating system, which is on top of the machine. Emulation is a different thing. Emulation is where I give you the look and feel of having this operating system, but I'm not really running the operating system. I'm running like a copy, like a version of the operating system that makes it feel like you have it. Like you could have an emulator for an Atari game. I don't know if you guys know what Atari is.
Yeah.
Still exists?
We don't.
No. So Atari is a company that made like computers for running games. And let's say they don't exist anymore. So you could have an emulator of an Atari system where, and because you want to run a game that only was made for Atari. So you emulate it on top of in your Windows operating system. You don't really replace your operating system. It just it's like a program that you run. It's just like any other program, but it does everything that it allows that is necessary in order to run a program written for an Atari.
Excuse me.
Yeah. Question?
Oh, I burped. I'm so sorry.
Okay, let's continue. Computing environments virtualization. I'm gonna skip that. Here we see a picture of what I was talking about. Here we have hardware operating system processes. And here we have, which is like this is like a regular computer. And here we have hardware, and this is a virtual machine manager is what I was calling a hypervisor. That's like a special operating system designed to manage multiple operating systems. And then you create in it a virtual machine 1, let's say, and then in that virtual machine, now you've got an empty machine. Basically, you install this hypervisor on top of your hardware. Then you say, I want to create one machine. So you create a machine. Now the machine is empty. It doesn't have an operating system. You need to install an operating system on it. And now you can run processes. Then you can say to this virtual machine manager, you can say, I want to create another machine. Call them V2, virtual machine 2. And you can install some other operating system on it. And you can create on top of this virtual machine manager as many virtual machines as you want.
And in each one, install whatever operating system you want. And this was very commonly, I don't know, when I used to work in this was very commonly done. This was like a big achievement, because before they had this, what did you have to do? If you wanted 2 different operating systems on your machine? We talked about it, we mentioned in the beginning of the class, dual boot. You could have a dual boot. You could, at boot up, you could choose which one you want, and then you could only run one or the other. In this setup, you could actually, without turning your computer on and off, you could go from one to the other. In the other dual boot, you need to turn your computer off. That's only at boot time. When you turn on the computer and you're booting it up, then you can choose which operating system. So this was a big innovation when it came about. Okay, another topic that is important in this course is real-time embedded systems. We're actually not going to spend that much time on this, but now I'm going to talk about this. Real-time or embedded systems are actually the most prevalent form of computers, even though you maybe don't even ever heard of it. Because, for example, you have one in your Kindle reader, in your washing machine, in an airplane, any device that has need to process, to decide, to make decisions and to do things. Like when you press on a button in a Kindle, there's a program that's doing something for you. So but it's embedded in the Kindle. You can't turn your Kindle into a calculator. I mean, maybe you could, but it's not a multi-purpose computer. It's a one-purpose computer. But also your washing machine, you can't turn into a calculator. It's got a computer in it, which calculates how much water you put in, and maybe it runs at a different speed based on how much clothes you put in. It runs maybe at different speeds depending on what temperature you rode or what, how much weight of clothing you put in. So these are called embedded devices, which means they're embedded into a piece of machinery. Like a car has embedded chips, we call them chips, processors, computers embedded in them, and they're called real time. What does it mean, real time? Real time means that time is a factor in the computation. For example, in a washing machine, if you want to calculate how long how much time it should take, how much I don't know, how much water you should put in this particular load, you need to calculate it before, at a certain time. You can't drag that calculation out too long. Or the best example is, let's say, a missile system. If you're shooting a guidance system for a missile, he needs to constantly correct the trajectory of the missile. But while he's calculating the change that needs to be made, the missile is progressing in its path. He's already in a different location. So your calculation was based on where he had been, but he's not there anymore. So your calculation is wrong. So you got to do it again. But by the time you finish the next calculation, it'll also have moved. So what do you got to do? You got to calculate. You got to say, the calculation is going to take me 5 seconds. Where will the missile be in 5 seconds? I'll calculate what change in trajectory I need to do in 5 seconds to get to where I need to go. And then I need to calculate it in 5 seconds. If it takes me 10 seconds, then the data is useless. So that's called a real-time system, a system that the time constraint. If I don't calculate it within a certain time, then the data is useless.
Could we please watch that video of the missile knows where it is? Because the missile knows where it is.
I don't know what video that is.
What are you guys talking about?
A video explaining that exact thing, which is.
I don't know that video.
YouTube is.
Somebody must have heard my discussion and made a video.
It's an amazing video.
Send me.
Are you admitting on recording that you watch YouTube?
I've been using that example for many years. That's the best example.
Yeah, it's a classic example. There's just a really classic reading of it.
All right, I'd be happy to. I'll look for it.
Lebanon should be blocked. Lebanon's also not appropriate.
So there are some computers that perform special tasks with an operating system and some without. In other words, you could have a real-time system without an operating system, just it runs a program. But there are operating systems for real-time systems. And it has a well-defined fixed time constraints. That's what I was explaining.
that there's a time constraint. Actually, the truth is, there's a distinction between hard and soft real time. What the missile case is like hard real time, where if I don't calculate it in the time allotted to me, then the data is completely useless. Whereas soft real time might mean that if I don't calculate it, it's still useful. It's still useful, but not really useful, or I don't know, it's hard to really think of an example of soft real time. Maybe the washing machine, where if I calculate a little bit wrong, the clothes will still get clean.
I'm a washing machine.
Okay. Now, there's this concept called open source operating systems, open source. Can anyone think of an example of an open source operating system?
Yes.
X.
Linux, what's a closed source? What does it mean that Windows is closed source?
That we can't see the code.
You can't see the code, right? Now, you just get, what do you get when you buy Windows? You get, what, you get a finished program, what do we call that? What?
Software.
Yeah, what else do we call it?
Executable.
Executable or compiled. We get after the compilation. Whereas source code means you got it before compilation. What's the advantage of having before compilation?
See what's going on.
You can see how it works and you could change it. You could alter it. Windows, you can't alter it. That's why we talked in the lab about Windows internals, because nobody really knows the internals. Even the internals that we talked about were not really internals, they were just programs that let you do some things. But the real internals of Windows, nobody knows. And if you work for Microsoft as on their operating system, you'll probably sign a non-disclosure contract where you can't tell anybody anything you know about it. Even though somebody was telling me about a video about a guy who wrote Task Manager, was that you guys? And he made a video about how it works.
Just come to that last class.
Okay.
That would be.
But that seems to be,
You know, you could play Fortnite on Windows.
I'm happy to hear that. But please, okay, counter. So against this idea of closed source was. So counter to the copy protection and digital rights movement, there's something called open source. In other words, one idea is that you have digital rights management and it's my thing and you can't use it, copy protection. So there's a thing called the Free Software Foundation, which has a thing called a copy, instead of copyright, they call it copyleft. And what does copyleft mean? It means you can use the work, you can modify it, distribute it freely on one condition, that anything derived from it is bound by the same condition, that you leave it open. In other words, that's why it's called left, because you leave it open. You don't, when you can't take, let's say, you're not allowed to, theoretically, you're not allowed, I think some people do, you're not allowed to take Linux and change it into a new version of Linux and then sell it, but only sell the compiled version and not let anybody know how you did it. If you want to use if you want to benefit from the free Linux,
Yeah, you would.
you have to sell the open source. You can sell the open source.
How can you sell the open source?
Because right, nobody would pay for it.
But I'm saying, if you took Linux, of course it may be illegal, but if you took Linux and you changed things in it, like slightly,
And then compile it.
and then compile it and then sell that, how do they know that it's not just your own operating system?
Oh, you claim it's not Linux. You
Right.
claim it's.
Because they can't see the code, so they can't verify that it's Linux,
What'd you say?
There might be, right, you're right. They might be able to compare the binaries.
of course.
Because if you didn't change it very much, then lots of the binaries would be the same.
Got it,
Well, Linux
okay.
is-
And
was
what
not.
really?
Nobody-
Linux
You thought Linux was bad?
And was exactly
The only thing I know about-
Actually.
All right.
You can ask Lena.
That's the end of this lecture.
Who's Linus?
Strategy is you make them never name it.
You make it or
Well, in English, it's Linus, not Linus.
You build your own compiler, which is called
Linus, I don't know, it's Linus.